The RSA algorithm is built around the idea that you can have multiple keys for encrypting and decrypting codes. There's the public key, which is used for encrypting the data, but it's known by everyone. And then there's the private key, which is used to decrypt the data, which is kept secret. So that's the basic idea, is that everyone has the key to encrypt the data, but only one person or one group can decrypt it. So we're going to be taking a look at the steps involved. So step one for this algorithm is you need to pick two distinct prime numbers, which will be called P and Q. So for security purposes, the P and Q need to be integers and chosen at random. So they should be kind of similar length, but they shouldn't be right next to each other on the number line. All right? And then what you do is you create the public key, and you create the public key by multiplying P by Q. And so the equation is n equals P times Q. So in our case, we'll make P equal 3 and Q equal 11. So that makes our public key equivalent to 33. All right? So there's some important things that have to be known when making the public key. The public key has to be larger than the value of m, which is the data that you want to encrypt. But we'll look at that in just a second. All right? What you also need is you need an exponent, okay? And this requires multiple steps. So the first step is to calculate the value of phi of n, okay? And it looks kind of scary doing this, but phi of n is Euler's totient function. So what it does is it takes the value of n, all right, and then it lists all the numbers that have the greatest common factor of 1 with n. So the only numbers that they have in common between a given number and n is 1. And it counts how many there are. So phi of n, if you're doing 9, all right? 9 has common factors with 3 and 6, and their common factors are 3, okay? But the rest of the numbers, which are 2, 4, 5, 7, and 8, have a greatest common factor of 1. So phi of n would equal 5 because there's 5 numbers that only have a greatest common factor of 1. Okay? So that's what phi of n equals. In this case, since our public key, which is n, is 33, phi of n is equal to 20 because there's 20 numbers that have greatest common factor of 1, and so it's just, yeah, that's what there is when it's 33. So once you get phi of n, to calculate our exponent, which is going to be e, our exponent has to be an integer, and it has to be greater than 1, but less than phi of n. So that's the first part of calculating e. It also has to have a greatest common denominator with phi of n of 1. So in this case, e has to be greater than 1 and less than 20, but its greatest common factor has to be 1. So they're relatively prime. Alright, so in this case, we are going to pick 3, because 3 is greater than 1, but it doesn't share any factors with 20. Alright? To determine our private key, which will be called d, the equation is e to the negative 1 mod phi of n. So the value of phi of n, which is 20. Mod stands for modular division, which essentially it's like normal division, except your answer is the remainder and everything else is forgotten. So if you're looking at how many times, if it's 10 divided by 3, it has a remainder of 1. So 10 mod 3 equals 1 because there's a remainder of 1. So it's e to the negative first mod phi of n. Okay? And so, yeah, that's what d equals. So it's going to be 3 to the negative first divided by modularly phi of n. Okay? There are multiple answers that could be d. So d is not a set thing. You kind of have to pick it. So there's multiple ways to get this. There's the equation I just gave you. Then there's d times e mod phi of n equals 1. And that's easier to pick a value for d. So in this case, we have multiple options. We can pick for d, we can get 13.667 times 3, which is our exponent, mod 20, that equals 1. And then 0.333 times 3 mod n, which is, so mod 20, is 1. And then there's 7 times 3 mod 20 is 1. So we're going to pick 7 because it's an integer. So just to summate what we're at, our first prime number is p, so that's equal to 3. Our second prime is 11. Our public key is 33. Our e is 3, and our private key is 7 because it's an integer and it's, yeah.